Something beneath Antarctica is broadcasting. We do not know what it is. We do not know how it is doing it. And the scientists who found it have spent nearly 20 years trying to explain it away, and failing. In 2006, a NASA balloon above the ice picked up a signal that was traveling in the wrong direction entirely. Not down from space, up from the ground, carrying energy so extreme it should have been destroyed, passing through the planet. It happened again, then again. 4 flights, nearly 2 decades. No confirmed explanation. Every theory that gets proposed leaves something unexplained. Stay until the end of this video, because the answer science is converging on is stranger than anything the conspiracy theorists invented. Subscribe and stay close, as this story continues unfolding. Another balloon is already being rebuilt. The ice sheet is still warping radio waves in ways we have not fully mapped. The anomaly is still threaded through 4 flights of data that no single theory has cleanly explained. And somewhere between the deepest part of the Earth and the instrument floating above it, a signal is still waiting for the exact right mind to finally tell us what it means. Here is something that should be impossible. And yet, it happened 4 times. In 2006, NASA and the National Science Foundation sent a balloon the size of a football stadium into the stratosphere above Antarctica. Not a rocket, not a satellite, a balloon. It floated at roughly 35 kilometers above the ice, high enough to see the curvature of the Earth, and it carried with it a set of antennas designed to do something that had never been done before at that scale. Listen, not for radio transmissions, not for weather data, not for signals from satellites. It was listening for the faint radio pulse produced when a ghost particle, a neutrino, slams into ice at nearly the speed of light. The experiment was called ANITA, the Antarctic Impulsive Transient Antenna. And from the very beginning, it was picking up things it wasn't supposed to. To understand why this matters, you need to understand what a neutrino is. Right now, as you are sitting there watching this, approximately 100 trillion neutrinos are passing through your body every single second. They come from the sun, from dying stars, from the faint glow of the Big Bang still echoing through the cosmos. They pass through you. They pass through the planet. They pass through virtually everything, which is exactly what makes them so difficult to study. Neutrinos are sometimes called ghost particles because matter, to them, is essentially invisible. The entire mass of the Earth is, for a neutrino, roughly as obstructive as a pane of glass. ANITA was designed to catch neutrinos of a very specific and extreme variety, ultra-high energy neutrinos. Particles carrying energy in the range of 1 exa-electron volt, that is 10 to the power of 18 electron volts. To put that into perspective, that is roughly the energy of a well-thrown baseball, compressed into a single subatomic particle. These particles are so energetic that when they occasionally do interact with matter, they produce a detectable radio pulse through a process called the Ascarian effect, where a cascade of charged particles creates a burst of coherent radio radiation. ANITA was floating above Antarctica specifically because Antarctic ice is extraordinarily radio transparent, making it the ideal medium for catching those pulses. Over 4 flights between 2006 and 2016, ANITA recorded exactly what scientists expected to find, and then something else entirely. On multiple flights, the instruments detected what appeared to be upward-going air shower events, signals that looked like the radio signature of a high-energy particle interaction, but coming from the wrong direction. Instead of arriving from above, from space, they were coming from below, from beneath the ice, as if something had traveled through the entire body of the Earth, emerged from the Antarctic ice sheet, and triggered a particle shower on its way out. Now, you might think, okay, perhaps it was a glitch. Perhaps it was instrument error, a reflection, a software artifact. Scientists thought the same thing. They checked, they rechecked, they ran the data through multiple independent analyses, and the signal remained. Between 2020 and 2024, the IceCube Neutrino Observatory, which we will come to in a moment, conducted its own analyses of the ANITA events. Their conclusion was careful and measured. The events might be consistent with rare background processes. Might be. Not were. Not definitely. And critically, no one has definitively dismissed them either. No confirmed alternative explanation has fully closed the case. And here's the part that should make you pause. If this were noise, if this were a well-understood instrument artifact or a statistical fluke, you would not be seeing continued investment in the problem. You would not be watching the construction of IceCube Gen 2, a major expansion of the underground detector array, or the development of PUEO, the payload for ultra-high energy observations, a next-generation balloon mission specifically designed to follow up on what ANITA found. Science does not spend hundreds of millions of dollars chasing dead ends. At least, not usually. The real issue, it turns out, is not just what the signal is. It is the direction it came from. And the direction, when you work through the geometry, is where this story starts to become genuinely uncomfortable. There is a mathematical formula that sits at the center of this entire mystery, and it is mercifully simple. The probability that a particle will survive traveling through a given material looks like this. P equals E to the power of negative sigma times N times L. You do not need to memorize that. What it means in plain language is this. The longer the path a particle travels through matter, and the more densely packed that matter is, the less likely it is to survive the journey intact. The probability drops exponentially. Every meter of rock, every kilometer of iron, every layer of dense mantle is another opportunity for that particle to interact with something and disappear. Think of it like trying to fire a bullet through the planet and have it come out the other side without hitting anything. Not slow down, not deflect, come out completely intact. At low energies, neutrinos can do something close to this because their interaction cross-section, their effective target size, is minuscule. But at ultra-high energies, that cross-section grows. The higher the energy, the more likely the neutrino is to interact with matter. And at exa-electron-volt energies, Earth is not transparent anymore. Earth is, for all practical purposes, a solid wall. The angles of the ANITA anomalous events imply that the particles responsible traveled through a significant chord length of the Earth's interior. We are not talking about a shallow graze. The geometry points to transit through thousands of kilometers of rock, mantle, and potentially the outer core, a region dominated by liquid iron, extraordinarily dense. The survival probability for a standard neutrino at those energies, through that path length, is not merely low. It approaches zero in any conventional calculation. Now, physicists did consider one partial escape route, and it involves tau neutrinos specifically. A tau neutrino can interact with matter, produce a tau lepton, which then decays and regenerates a new tau neutrino, slightly lower in energy, but continuing forward. Scientists call this leapfrogging. It is a real process. The tau neutrino essentially passes the baton to its decay products, which then carry a new neutrino forward through the Earth. In theory, this could allow a tau neutrino to survive longer path lengths than other flavors. In practice, the predicted rates of events arriving at ANITA's geometry from this process are extremely small. Not zero, but small enough that seeing multiple events of this type across 4 separate flights strains the calculation considerably. The numbers do not comfortably fit. What you are left with is a handful of events. Not hundreds, not thousands. Just a handful that appear to come from the wrong direction, at energies that should not permit survival through the Earth, with no confirmed explanation for what produced them. The small number is important to keep repeating. This is not a flood of anomalous signals. This is a trickle. But a trickle at energies that should not exist is, scientifically, more alarming than a flood of signals that make sense. The geometry tells you something had to travel through the Earth. The energy tells you nothing we know of can do that. And the statistics tell you this probably is not a coincidence, though the margin for doubt remains real. So if ANITA is seeing these events, the obvious question is, why isn't the most sensitive neutrino detector ever built, buried right there in the same Antarctic ice, seeing them too? Why is IceCube silent? IceCube is one of the most extraordinary scientific instruments ever constructed by human beings, and it is almost entirely invisible. Buried beneath the South Pole, between 1,400 and 2,450 meters below the ice surface, IceCube consists of over 5,000 individual optical sensors arranged along 86 vertical strings. Those sensors are spread across a full cubic kilometer of ancient Antarctic ice, and they are waiting in the dark and cold for a specific kind of light. When a neutrino interacts with the ice or the bedrock below and produces a cascade of fast-moving charged particles, those particles emit a faint blue glow, a phenomenon called Cherenkov radiation, and IceCube's sensors catch that light. IceCube has been genuinely, spectacularly successful. Since 2013, it has confirmed the existence of a diffuse flux of astrophysical neutrinos arriving from outside our galaxy. It has linked specific neutrino detections to individual blazars, supermassive black holes firing jets of plasma directly at Earth. It has transformed neutrino astronomy from a theoretical exercise into an observational science. And when IceCube analyzed the sky regions and energy ranges corresponding to the ANITA anomalous events, it found no matching signal at the rate you would expect if those events were real tau neutrinos of the type ANITA seemed to detect. Now this is where the story gets more nuanced, because the absence of a signal in IceCube does not automatically mean ANITA is wrong. These two instruments are not doing the same thing in the same way. ANITA is a radio detector floating in the stratosphere, looking down at a continent-sized sheet of ice. Its acceptance geometry, the range of arrival directions and energies it can plausibly detect, is enormous. It sees a huge volume of the horizon. IceCube, by contrast, is embedded in the ice itself, looking for optical light from interactions happening within or just below its array. Its geometry is fundamentally different. The Ascarian effect that ANITA relies on, the radio pulse from a particle shower, is produced by charge imbalance in the shower front. ANITA is capturing that radio emission from high altitude. IceCube is looking for optical photons from interactions inside its fiducial volume. These are different windows onto the same phenomenon. There is also a more uncomfortable explanation for the ANITA events that a number of physicists have taken seriously: reflection. Antarctic ice is not a uniform medium. It has internal layers, density gradients, a compressed upper zone called the Fearon layer, and a phenomenon called birefringence, where the crystal structure of the ice splits polarization states of radio waves. A downward-going cosmic ray air shower arriving from above could, in principle, reflect off the ice surface and mimic an upward-going signal. The polarization of the reflected signal would be inverted relative to the original, and this is something ANITA should be able to detect. Some of the anomalous events do not show the inverted polarization expected from a simple surface reflection, which is why the debate continues. But ice is complicated, and complicated media do complicated things to radio waves. What this means is that ANITA and IceCube are not contradicting each other in a simple way. They are probing different parts of a parameter space that is genuinely difficult to map. Neither instrument has the full picture, and the absence of a signal in one place does not cleanly explain away the presence of a signal in another, which means the question has to go somewhere else. If neither instrument is simply wrong, then maybe what is wrong is the model we are using to understand what particles can and cannot do. And that is where this investigation opens into something much larger. The Standard Model of particle physics is one of the most precisely tested theories in the history of science. It describes all known fundamental particles and 3 of the 4 fundamental forces of nature. Its predictions have been confirmed in experiments to astonishing decimal precision. When the Higgs boson was discovered at CERN in 2012, it was the last missing piece of the Standard Model predicted decades earlier, and its properties matched theoretical expectations almost exactly. By every conventional measure, the Standard Model works, and yet, physicists have known for a long time that it is incomplete. It says nothing about gravity at the quantum scale. It does not explain dark matter or dark energy. It does not explain why matter dominated over antimatter in the early universe. The Standard Model is a triumph and a frustration simultaneously. One of the most popular proposed extensions is called supersymmetry, or SUSY for short. Supersymmetry predicts that every particle in the Standard Model has a heavier partner particle, a superpartner, with slightly different quantum properties. The electron has a selectron, the quark has a squark, and the tau lepton, the heaviest of the charged leptons, has a partner called the STAU. The STAU hypothesis for the ANITA anomaly goes like this. A highly energetic cosmic ray or neutrino interacts somewhere deep inside the Earth and produces a STAU, a long-lived supersymmetric particle that interacts only weakly with matter. Because it barely interacts, it can travel through thousands of kilometers of rock more easily than a standard neutrino at EeV energies. It exits near the Antarctic surface, decays, and produces an upward-moving air shower that ANITA interprets as a particle cascade. Problem solved. No physics violation, just new physics. It is an elegant solution. The STAU has been seriously proposed in published, peer-reviewed papers as an explanation for the ANITA events. The mathematics can be made to work in certain parameter regimes. Here is the problem. The Large Hadron Collider at CERN has been running for over a decade, colliding protons at energies that should be more than sufficient to produce superpartners if they exist in the mass range most theories originally predicted. And it has found nothing. Not a single confirmed SUSY particle. Every search has come up empty, and the parameter space where supersymmetry can comfortably hide has been shrinking steadily with every run. That does not mean SUSY is dead. It means the simple versions of it are under serious pressure, and the versions that could explain ANITA require very specific mass and lifetime parameters for the STAU that have not been ruled out, but have also not been confirmed anywhere. You also have to ask, why Antarctica? Why not anywhere else on the planet? A STAU, produced by cosmic ray interactions deep in the Earth, should be producible anywhere. If this mechanism were real, you might expect to see upward-going events from other experiments around the world. So far, none have been reported with the same character as the ANITA events. The STAU hypothesis is alive. It is not confirmed. And it may never be, because the instrument designed to test it more rigorously, PUEO, has not yet flown its primary mission. The answer to whether new particles are involved may still be years away. But there is a quieter explanation, one that does not require inventing new particles at all, and in some ways it is more unsettling than new physics. It suggests that something we think we already know might be wrong. Here's a fact that most popular science coverage quietly glosses over. We have never directly measured how neutrinos interact with matter at EeV energies. Not even close. The highest energy neutrino interactions we have ever measured in a laboratory setting are many orders of magnitude below the energies implied by the ANITA events. When physicists calculate what a neutrino should do at 10 to the 18 electron volts, they are not reading off a table of experimental results. They are extrapolating. They are taking measurements from lower energies, plugging them into theoretical frameworks, and extending the curve into territory no experiment has ever directly explored. The key quantity is called the neutrino-nucleon cross-section, essentially how big a target a neutrino looks like to the quarks inside an atomic nucleus when they collide. At low energies, this is well measured. At higher energies, it grows, following predictions derived from what physicists call Parton distribution functions. mathematical descriptions of how momentum and energy are distributed among the quarks and gluons inside a proton. At extremely high energies, the behavior of these distributions is governed by a phenomenon called small x physics, where x represents the fraction of the proton's momentum carried by the interacting parton. At small x, the proton looks like a sea of gluons, and the number of those gluons grows rapidly as you go to lower x values. At some point, physicists expect this growth to saturate, to slow down, because gluons cannot keep proliferating indefinitely without recombining. This is called gluon saturation. If gluon saturation kicks in at sufficiently high energies, the neutrino cross-section would grow more slowly than standard extrapolations predict. And if the cross-section grows more slowly, the Earth becomes more transparent to ultra-high energy neutrinos than our current models assume. Particles that our calculations say should interact and disappear on their way through the Earth might, in a saturated gluon regime, have a slightly better chance of making it through. No new particles required. Just a correction to physics we already know exists, but have not fully mapped at the relevant scales. This is an active area of theoretical research. Papers have been written proposing that revised cross-sections could partially accommodate the ANITA anomaly. The numbers are difficult to make work completely, but they reduce the gap between what is observed and what is predicted. More importantly, this would not just affect the ANITA puzzle. It would cascade through the entire framework of ultra-high energy cosmic ray physics, changing how we interpret the most energetic events in the universe. Every calculation about particles arriving from distant galaxies would need revisiting. That is the scale of what is potentially at stake. Not just one anomalous detector in Antarctica. The entire theoretical scaffolding we use to understand the highest energy processes in the cosmos. And yet, even this explanation, appealing in its minimalism, requiring no new particles, just revised parameters, may not be enough on its own. Because the neutrino, it turns out, might itself be more complicated than the three-flavor picture we have been working with for decades. The neutrino was once thought not to exist at all. When Wolfgang Pauli first proposed it in 1930, he called it a desperate remedy, an invisible, massless particle he invented to save the law of energy conservation, and he genuinely doubted it could ever be detected. He was wrong about the detection. He may also have been wrong about how simple neutrinos are. We now know there are three confirmed flavors of neutrino: the electron neutrino, the muon neutrino, and the tau neutrino. And we know they are not fixed. A neutrino produced as an electron neutrino can, over time and distance, become a muon neutrino, then a tau neutrino, then back again. This is called neutrino oscillation, and it was one of the first confirmed violations of the original Standard Model, which predicted neutrinos should be massless and should not oscillate at all. But here is where it gets more interesting. In matter, dense matter, like the interior of the Earth, the oscillation probabilities change. Electrons in the rock interact with electron neutrinos specifically, modifying the effective mass and mixing angles. This is called the MSW effect, after Mikheyev, Smirnov, and Wolfenstein. Matter itself reshapes how a neutrino oscillates as it travels. Now some physicists have proposed the existence of a fourth type, the sterile neutrino, a particle that carries no charge, interacts through none of the four fundamental forces except gravity, and is essentially invisible to every detector we have ever built. It would not interact with electrons in rock. It would not produce Cherenkov light in ice. The only way you would ever know it existed is through its effect on the other neutrino flavors it mixes with. The sterile neutrino hypothesis for ANITA goes something like this. An ultra-high energy neutrino enters the Earth, and as it travels through the planet's interior, oscillations driven by the MSW effect cause it to transition partially into a sterile state. In the sterile state, it is effectively invisible to matter. It cannot interact. It cannot be absorbed. It passes through freely. As it approaches the surface, oscillation conditions change, and it transitions back into an active flavor, emerging near the Antarctic ice and producing the shower ANITA detected. It is a clever mechanism. It uses known physics, oscillations, matter effects, extended into a speculative but theoretically motivated framework. The problems are significant. Cosmological observations, particularly from the Planck satellite's precise mapping of the cosmic microwave background, place tight constraints on how many neutrino species can have existed in the early universe. Additional neutrino species with certain mass ranges would have left detectable imprints on the structure of the cosmos. Planck's data disfavors sterile neutrinos in many of the mass and mixing angle regimes that would be useful for explaining ANITA. None of this is a definitive ruling out. Parameter space survives. But the gaps where sterile neutrinos can hide and still explain ANITA without contradicting cosmology are narrow. What this means is that every exotic particle explanation for the ANITA anomaly carries the same warning label: possible, theoretically constructed, not confirmed. But the fact that multiple separate theoretical frameworks, Stau particles, cross-section revisions, sterile neutrinos, can each be plausibly aimed at this anomaly says something important. It says the anomaly is genuinely sitting at the boundary of what we understand. And then there is a possibility that none of these particle physics explanations fully address. What if the issue is not what the particle is, but where it came from? What if Antarctica itself is part of the equation? Antarctica is not simply a place where cold things happen. The ice sheet covering the continent reaches depths of nearly 3 kilometers in places, and it is among the most radio-transparent natural materials on Earth. That transparency is exactly why ANITA was sent there. But transparency is not the same as simplicity. Ice, when you look at it carefully, is a remarkably complex medium for radio wave propagation, and that complexity introduces possibilities that took years for the physics community to fully appreciate. The upper layer of the Antarctic ice sheet is not solid ice. It is a gradually compacting layer of compressed snow called firn, and it spans roughly the top 100 meters of the sheet. Within the firn, the density of the medium increases with depth, which means the refractive index, the measure of how much a wave bends as it moves through a material, also changes with depth. Changing refractive index means radio waves do not travel in straight lines through firn. They curve. Under the right conditions, a signal entering the firn at one angle can exit at a different angle, potentially mimicking the arrival direction of an upward-going event when it was actually a downward-going one. There is also the question of birefringence. The ice crystals deep in the Antarctic sheet are not randomly oriented. Over centuries of compression and flow, they develop preferred alignments, and this alignment means the ice behaves differently for radio waves with different polarization orientations. A single incoming radio pulse can be split into two components, traveling at slightly different speeds, arriving at a detector offset in both time and phase. For an instrument like ANITA, trying to reconstruct the polarization state of an incoming signal, which is crucial for distinguishing reflected cosmic ray signals from genuine upward-going events, birefringence is a source of genuine interpretive difficulty. Beneath the ice, the situation adds another layer of complexity. Antarctica harbors over 400 known subglacial lakes, the most famous being Lake Vostok, a body of liquid water the size of Lake Ontario, sitting beneath roughly 4 kilometers of ice. The boundaries between ice, water, and bedrock create interfaces with very different radio reflection properties. A signal bouncing between subglacial layers could, in principle, be redirected in ways that standard flat surface reflection models do not account for. Researchers have argued that some fraction of the ANITA anomalous events could be cosmic ray air showers arriving from above, producing radio pulses that reflect off the ice surface and mimic upward-going events. Surface reflections should invert the polarity of the signal, and ANITA is designed to detect this. Some anomalous events do not show the expected polarity inversion. That is the crux of the debate. Ice birefringence and subsurface scattering could potentially alter polarization in ways that complicate this test, but no fully worked out model has successfully reproduced the anomalous events through ice effects alone. So the ice is a complicating factor. It makes interpretation harder. It creates genuine ambiguities that have fed years of debate. But here is the critical point. No known property of Antarctic ice produces EeV-scale particle showers. The ice can distort signals. It cannot create them. Whatever the source of these events is, it is not the ice itself doing the broadcasting, which means we have to look elsewhere. And one direction that has received surprisingly little public attention is straight up toward the sun. The sun is not a constant star. It pulses on an approximately 11-year cycle, moving between periods of relative calm, solar minimum, and periods of intense magnetic activity called solar maximum. During solar maximum, the sun produces more frequent and more powerful solar flares, coronal mass ejections, and streams of high-energy charged particles. This solar wind does not just affect satellites and power grids. It affects the environment of near-Earth space in ways that ripple down through the magnetosphere and into the upper atmosphere. Ultra-high-energy cosmic rays, the most energetic particles arriving from outside the solar system, are not significantly deflected by the sun's magnetic influence because their energies are so extreme that the relatively weak interplanetary magnetic field barely curves their trajectories. But the lower energy cosmic ray background, the constant rain of particles arriving from our galaxy, is modulated by the solar cycle in measurable ways. During solar maximum, the increased outward solar wind partially shields the inner solar system from galactic cosmic rays, reducing the flux arriving at Earth. This is called the four-bush decrease, when it happens suddenly, driven by a coronal mass ejection sweeping past Earth and temporarily compressing the cosmic ray environment. Here's where it gets speculative, but worth examining. ANITA's 4 flights spanned from 2006 to 2016, a period that included the unusual and prolonged solar minimum between solar cycles 23 and 24, one of the deepest solar minima in nearly a century. This period, from approximately 2007 to 2009, saw unusually low solar activity, reduced solar wind pressure, and a measurably increased influx of galactic cosmic rays into the inner heliosphere. Could an altered cosmic ray environment during unusual solar periods affect the background rates of high-energy events in ways that might create or exaggerate anomalous signals? The honest answer is that no one has firmly established this connection for the ANITA anomaly. The data are sparse. The flights were not timed to probe solar cycle effects. The correlation, if it exists, has not been demonstrated in a statistically meaningful way. What is genuinely unique about the South Pole as a detection site is its relationship with Earth's magnetic geometry. The geomagnetic pole is not precisely at the geographic pole, and the field geometry at high southern latitudes differs meaningfully from mid-latitude sites. The atmospheric cascade development of cosmic ray air showers, the extended chain reaction that produces the radio signals ANITA captures, depends in subtle ways on the local magnetic field, because the secondary particles in the shower are charged and their trajectories are bent by magnetism. Near the pole, this geometry is unusual, and the effects on shower development are not fully characterized in all simulation codes. None of this amounts to an explanation. There is no established mechanism linking solar activity or polar magnetic geometry to the ANITA anomalous events in a way that would account for their energy and arrival direction. But the South Pole is not a generic location. It is magnetically singular, and the instruments deployed there are sensitive to effects that mid-latitude detectors would never encounter in the same form. And then there is one more possibility, the most controversial one, the one that almost nobody in the mainstream physics community takes seriously, but which, if you follow the geometry to its logical extreme, is technically worth stating, even just to dismiss it properly. let us be absolutely clear about something before we go any further. There is no established scientific evidence that Earth's interior is generating exa-electron-volt particle events. None. The physics of Earth's core and mantle, as we understand it, does not include any process capable of producing particles at those energies. This is not a suppressed finding. This is not something scientists are quietly hiding. It is simply not something that known geophysics can do. And yet, the geometry of the ANITA anomalous events points at the ground, not at the sky. And when you are doing science and the geometry points somewhere unexpected, the intellectually honest move is to at least describe the space of possibilities, even the ones that seem implausible, before ruling them out with evidence. The Earth's interior is poorly understood in ways that would surprise most people. We have never drilled below about 12 kilometers into the crust. The deepest hole ever made by human beings, the Kola super deep borehole in Russia, reached just over 12 kilometers and took decades. The mantle begins around 30 kilometers down and extends to approximately 2,900 kilometers. The outer core is a region of liquid iron and nickel, beginning there and running to about 5,100 kilometers. The inner core below that is solid iron under pressures and temperatures so extreme that our understanding of the material properties involved is based entirely on seismic wave analysis and computational models, never direct measurement. We know the structure of Earth's interior the same way a blind person might know the layout of a room, by tapping on the walls and listening to the echoes. Seismic tomography, using earthquake waves, has revealed structures within the mantle that remain poorly explained, including large low shear velocity provinces deep in the lower mantle beneath Africa and the Pacific, sometimes called LLSVPS, or somewhat dramatically, the blobs. What they are made of, how they formed, and what role they play in mantle dynamics is genuinely unresolved. Neutrino tomography, using Earth-traversing neutrinos to map the planet's interior density, variations the way X-rays map a body, is an emerging and legitimate field. IceCube has already produced early results using atmospheric neutrinos to probe Earth's density profile. The concept of using neutrinos to look inside Earth is real, and it works. None of this implies Earth is generating the ANITA signals. Extraordinary claims require extraordinary evidence, and there is no evidence here for a geophysical source. But it frames something important. The Earth's interior, the very medium these signals allegedly traversed, is not as well understood as a physics textbook might lead you to believe. What we can say is this: the ANITA anomaly, whatever it turns out to be, has inadvertently highlighted how many unresolved questions sit at the intersection of particle physics, astrophysics, and planetary science simultaneously. It is not just a question about one weird signal from one balloon. It is a thread that, when pulled, unravels into the structure of matter, the interior of planets, and the limits of what our instruments were designed to see. So how did it take nearly 2 decades for any of this to reach the broader public? That question has an answer, and it says something uncomfortable about how science actually works. Science has a speed problem that has nothing to do with incompetence. The ANITA collaboration identified anomalous events years before they reached wide public awareness. The first papers describing the strange upward-going events were published in 2016 and 2018. They were immediately read by specialists. They generated significant discussion within the particle physics and astrophysics communities. And then they sat. Not because anyone was hiding them, because the norms of frontier physics demand an extraordinary level of caution before anything gets promoted as potentially significant. The core issue is small number statistics. When you are dealing with a handful of events, and the ANITA anomaly involves literally a few events across 4 flights spanning a decade, the statistical framework for claiming significance is brutally demanding. In particle physics, a discovery requires what is called 5 sigma confidence, meaning the probability of the signal arising by chance is less than 1 in 3.5 million. A result sitting at 2 or 3 sigma is considered interesting but not significant. The ANITA anomaly, by most analyses, sits somewhere in that ambiguous zone. Within scientific collaborations, this ambiguity generates years of internal debate. Were the events properly reconstructed? Were the backgrounds correctly estimated? Were there systematic errors in the polarization analysis? Every component of the signal reconstruction gets scrutinized by people whose careers depend on not claiming new physics prematurely. The scientific community is haunted by cases where apparent anomalies evaporated under scrutiny. The faster-than-light neutrino claim from the OPERA experiment in 2011 being perhaps the most memorable recent example, caused by a loose fiber optic cable. There is also the funding dimension. The teams involved in ANITA and IceCube are competing for limited resources in a field where proposals are judged partly on how well you justify your instrument's scientific case. Claiming too loudly that you have found something inexplicable can cut both ways. It can generate excitement and support, or it can make review panels nervous about funding experiments chasing unverified anomalies. The institutional incentives are complex. And then there is peer review itself, which is the correct and necessary gatekeeper of scientific claims, but which operates on timescales measured in months to years, not days. A result that needs to be cross-checked by independent collaborations, reanalyzed with different methods, and placed in the context of theoretical frameworks being developed simultaneously does not move fast. What changed was not the science. The underlying papers were available to anyone who wanted to read them. What changed was attention. A series of physics blogs, science journalists, and eventually mainstream media outlets began connecting the dots around 2019 and 2020, pulling the ANITA papers into a narrative that general audiences could follow. The story did not surface late because it was suppressed. It surfaced late because genuine scientific uncertainty is not a story until someone decides to tell it. And when genuine uncertainty meets public attention, something predictable happens. The space that science leaves open with the words we do not yet know fills up, not always with good things. Antarctica is one of the most powerful magnets for conspiratorial thinking on the planet, and it is not entirely difficult to understand why. The continent is governed by the Antarctic Treaty System, signed in 1959 by 12 nations, and now ratified by over 50. The treaty designates Antarctica as a scientific reserve, bans military activity and nuclear testing, and restricts full sovereignty claims. Access to the continent is limited by logistics and cost, not by legal prohibition. Any nation can conduct scientific research there, but for most people, it might as well be the moon. Remote, cold, controlled, inaccessible. That combination of remoteness and institutional oversight creates the atmospheric conditions for myth. Stories about hidden Nazi bases beneath the ice, which trace back to genuine but mundane wartime operations, have circulated for decades. The Hollow Earth theory, which long predates Antarctica's scientific exploration, has found a southern home in various tellings, with claims that the continent sits above an entrance to a subterranean world. Ancient civilizations buried beneath the ice. Secret bases operated by unnamed global powers. And now, conveniently, a signal coming from beneath the ground that mainstream science cannot immediately explain. When the ANITA anomaly entered popular awareness, it was almost immediately absorbed into these existing narratives. The framing became, scientists found something they cannot explain and are not telling you the full story. The gap between what is known and what is unknown was read not as scientific uncertainty, but as concealment. This is worth addressing directly, because the people making these claims are not being irrational in the broadest sense. They are pattern matching against a template of institutional distrust that has been reinforced by enough real historical examples of suppression and secrecy that it cannot be entirely dismissed as paranoia. The problem is calibration. The conspiratorial reading requires that hundreds of physicists across multiple independent institutions in multiple countries are coordinating a suppression of findings, while simultaneously those findings are published in open access journals that anyone can read for free. The physics alone, without any exotic overlay, is genuinely extraordinary. A signal that cannot be definitively explained by the most sensitive instruments ever built, at energies that challenge our models of how matter interacts across multiple independent flights in the most extreme environment on Earth, that is already a remarkable story. It does not need embellishment. An embellishment in this case does the opposite of illuminating the mystery. It buries the actual science under a layer of noise that makes it harder to think clearly about what is real. The anomaly is real. The uncertainty is real. The extraordinary is already present in the data, in the peer-reviewed record, in the ongoing construction of the instruments being built to follow up. None of that requires a secret. It only requires patience, which is, admittedly, the thing science demands most and popular culture supplies least. What happens next is the part of this story that might actually be resolved within our lifetimes. We are standing at a fork in a very unusual road. In the next 5 to 10 years, two major instruments are going to dramatically increase our ability to either confirm or rule out the ANITA anomaly. IceCube Gen 2 will expand the existing detector volume at the South Pole from 1 cubic kilometer to roughly 10 cubic kilometers, adding radio detection arrays to complement the optical sensors already in place. This is not a modest upgrade. It is an order of magnitude increase in sensitivity, specifically designed to probe the ultra-high energy neutrino regime, where ANITA found its strange events. PUEO, the payload for ultra-high energy observations, is the dedicated next-generation balloon mission designed as ANITA's successor, with improved sensitivity, better angular resolution, and more sophisticated polarization analysis to address the exact ambiguities that have kept the anomaly unresolved. These instruments will either find more events with the same character as the ANITA anomalies, at rates that demand explanation, or they will find nothing, setting limits that push any exotic explanation into increasingly implausible corners. The first future goes something like this. The anomalous events turn out to be rare cosmic ray reflections, interpreted incorrectly due to the complex interaction of Antarctic ice with radio waves at extreme energies. Statistical fluctuation played a role. Our understanding of ice birefringence and subsurface reflection was incomplete in ways that have now been corrected. The ANITA events will be remembered as an important lesson in the difficulty of interpreting signals from novel radio detectors operating in environments that were not fully characterized at the time of deployment. Science advances, models are refined, and the question closes without requiring any revision to fundamental physics. That outcome would not be a failure. It would be science working correctly, building more sensitive instruments, finding the error, and updating. Journals would publish the resolution. The community would move on. The universe would be exactly as strange as we already thought. The second future is harder to describe because it opens into territory that is genuinely uncharted. If IceCube Gen 2 and PUEO see the events at rates consistent with a real astrophysical signal, and the events cannot be explained by surface reflections or background processes, even with improved instrumentation, then something in our understanding of particle physics is wrong. Not tweaked, wrong. The cross-section revision scenario would require rewriting particle transport codes across the entire field of ultra-high energy astrophysics. The sterile neutrino scenario, if it survived cosmological constraints, would add a new particle to the census of nature. The supersymmetric scenario would be the first confirmed detection of physics beyond the standard model after decades of searching, with all the implications that carries for our understanding of dark matter, the early universe, and the unification of forces. And here is what that would mean, at the largest possible scale. Neutrinos are messengers. They travel across the universe, from the most violent events in existence: gamma-ray bursts, the cores of active galaxies, the shockwaves of supernovae, without being deflected or absorbed by the matter and magnetic fields that block every other form of radiation. If our model of how neutrinos interact with matter is wrong in the ways the ANITA anomaly suggests, then every measurement we have ever made using astrophysical neutrinos as probes is affected. The cosmic map we have been drawing, using ghost particles as our pencils, would need to be redrawn. 3 kilometers beneath the Antarctic ice, thousands of optical sensors are suspended in the dark, waiting for photons that carry information from across the galaxy. A stratospheric balloon drifted above the same continent for multiple flights across a decade, trailing antennas designed to catch radio whispers from the most energetic events in the universe. And instead of receiving clean, expected signals from above, those instruments caught something rising from below. Most likely, it was the ice, or the statistics, or an instrument artifact that improved technology will eventually characterize and close. Probably. But probably is doing a lot of work in that sentence. And the history of physics is littered with anomalies that everybody assumed were probably nothing, right up until the moment they turned out to be everything. We built instruments sensitive enough to hear the universe whisper. Something whispered back from the wrong direction. And the most extraordinary thing about this story is not the signal. It is the fact that after nearly 2 decades, with all the tools of modern particle physics and astrophysics pointed at the question, the answer is still, we are not certain. In science, that uncertainty is not an ending. It is an invitation, and somewhere beneath the ice, the signal is still waiting to be understood.